So it's a real pleasure to have Nina Balcan here as our distinguished lecturer speaker. Nina is a Cadence Design Systems Professor of Computer Science at Carnegie Mellon University. She's well known for her foundational work in machine learning, including foundations of active learning, semi-supervised learning, noise-tolerant learning, her work bringing together learning theory and game theory, including the first work on machine learning for mechanism design, and more recently spearheading the use of machine learning in the design of algorithms themselves. Most recently on theory for verification of LLM reasoning that she'll talk some about today. She served as program chair for all three of Colt, ICML, and NeurIPS, the only person ever to have done so. And she's still alive. And general chair for ICML, and in many years IMLS board member. That's the board that runs ICML conference. She's also been invited speaker at the International Congress of Mathematicians, the International Conference on Game Theory, where laureates give their talks. She's been a fantastic advisor to PhD students, producing a number of amazing students, including two here, Sid Prasad, RIP here, and Ravi Sharma, a postdoc. She's won a number of awards. I'm not going to list them all, but I'll just highlight her winning the ACM Grace Murray Hopper Award for her foundational and breakthrough contributions to minimally supervised learning. She's also a fellow of the ACM and Triple AI. And let me just add, she's someone I personally aim to emulate in my thinking the best I can.
Okay, all right. Thank you, Akim, for the introduction. Okay, and thank you for the invitation to give a talk here. I guess this talk is about the theory of modern AI, and in particular about some new learning theoretic, game theoretic, and algorithmic perspectives that we developed in my group over the past few years. And I put a disclaimer. I've given many talks throughout the years in this TTIC. All of them including proofs. Today we're not going to have any proofs. So it's more a bit of a higher level talk. All right. So I'm happy to talk about proofs offline as much as you want. Cool. So okay. So we all know machine learning and AI are everywhere. Are ineluctable, inevitable, inescapable, and unstoppable. So we know all of that. Also, as probably all here know, machine learning and AI are used currently for much more complex tasks than people were doing even 3 years ago or even a year ago. So, for example, they have been recently used for solving non-trivial math problems, like International Math Olympiad problems written in plain text. The agents use AI and machine learning tools for planning all sorts of things like trips and events. And there has been recently hope that these AI systems will somehow be able to propose and carry out very meaningful and innovative research agendas on their own. Okay, so much more complex tasks than ever before. Learning these days happens in the presence of many other potentially learning agents that might be very sophisticated agents. So, for example, in the context of security applications, both the attacker and the defender might be using very sophisticated machine learning systems. And finally, AI is now currently used for much more high-stake domains than before. So people talk about using them pervasively in medical domains, in banking, and also diplomacy and international relations. So as high stakes as they can get, these domains are these days. Okay. On the other hand, our theoretical understanding of these AI systems and machine learning systems is much more limited. So, for example, classic machine learning theory addresses kind of the case where you have a single learner in its own world learning potentially a very simple task. Now, to be fair to this classic theory, it has been powered by very beautiful and amazing and seminal results in both optimization and algorithms, and also in statistical learning theory and empirical processes. And these theory results actually were important to getting machine learning where it is today. However, obviously, these results are far from being applicable to like the future or the current or even the future, definitely the future AI systems. Okay. As another example, when you think about multi-agent systems, say from a game theory perspective, so historically, people think about like static solution concepts, like equilibria. And when learning is involved, it's often, the classic results often think about very simple learners, very simple learning algorithms, because these learning algorithms in game theory are derived thinking about human agents, which are much less sophisticated. Okay? And then finally, as another example about limitations of theory, in AI, and I guess throughout computer science and science in general, algorithms, which are obviously important, have been historically hand designed, and we often enforce case guarantees, which again are kind of insufficient for the modern AI. Okay, and so in this context, where current AI systems are considering, in current AI systems, we have many potentially sophisticated learners learning sophisticated, complicated, complex things in the presence of other learners, and AI systems are used for potentially much more high-stake domains. Obviously, you have to develop kind of new theoretical foundations, and to do so, we need to obviously use a kind of a multifaceted approach, and to use and I guess to build on and extend on ideas from many different fields, including like learning theory, game theory, algorithms, and so on, and that hopefully that will help us analyze and design better AI systems. Okay, and maybe this crowd here doesn't ask this question, but why would we want to do theory at all, theory of AI at all? The best way to summarize, I was thinking by a quote, so there is a very famous Romanian soprano that I really love. Her name is Angela Gheorghiu. She says, pop music is for the body, but opera is for the soul. So by comparison, you might think, well, AI is for the body, for the real world, but theory of AI is for the soul. But I disagree with that. I think theory of AI is both for the real world and the soul, so it's for both. Okay, so if we understand better, if we can develop better theory for AI, we can hopefully design better AI systems and to impact the real world, in addition to being intellectually very exciting. Cool, so with this introduction, so for the rest of the talk, I'm going to tell you some, I guess, concrete results in a couple of directions. So the first one is learning in the presence of other learners. And here I'll talk both about, I guess, cooperative situations. So for example, we have a generator and a verifier cooperating in the context of chain of thought reasoning, so, and LLMs. And so, and I'll also talk about, mention some of our results in on learning is the presence of other learners in strategic situations with commitments, tackle kind of games in particular. And if at this time, I'm going to briefly mention also a work on learning other complex objects, namely learning algorithms and solving problems that remain hard in classic frameworks. Okay, so in this introduction, I can start talking about the very first topic. And the first topic is on learning verifiers for chain of thought reasoning. And again, what to watch out for here in the end is like we'll have multiple agents, the verifier and the generator, and well, hopefully there will be a cooperation involved. Okay, and this is basically joint work with several TTIC people, including Avrim, Ioanzi, I saw him right there, and Dravi. Okay, cool. Oh, he's over there, yeah. Good. All right, so learning verifiers for chain of thought reasoning. So here's the motivation. So I guess everybody here probably knows LLMs with chain of thought reasoning has been, I mean, it's currently used pervasively in many situations. For example, for answering mathematical questions, in the context of agents for planning events, and so on. Now, the issue is that these, I mean, these current LLMs are still making mistakes, and learned verifiers that, for natural language, so verifiers that can verify natural language can help correct such mistakes. And in fact, it's some of the I guess are called frontier systems like DeepSeek, MapV2, and so this is I guess system from DeepSeek. They're mapped to system for solving math questions. And similarly, this Alethea system powered by Gemini DeepThink. So they actually acknowledge that they use verifiers, learned verifiers, for improving the LLM-generated solutions. So DeepSeek with Math V2 is for math, and this Alethea system is a recent system posted by DeepMind, is for like autonomous math research. And so both of these systems acknowledge that the learned verifiers are the key component for helping correcting mistakes of their generators. Okay, and now even if you live in a world, and some of my colleagues at CMU do believe so, that these systems will soon be so good that they're never going to make mistakes. Even then, I think having verifiers can be important because they can increase confidence in very critical, very high-stake domains. So like I like to say, I'm a very cautious person, so even if the system is fantastic, if I could use a verifier to verify the solutions, convince myself it's a great system, I'll gladly use it. Okay, and then finally, as another motivation here, as some of you are aware, actually many conferences, including machine learning and theory conferences and algorithmic game theory conferences, have offered this in the past cycle a pre-submission verification service. So and they're all LLM based. So basically, a week before the deadline, if you had your paper, you could submit your paper, and they'll give you feedback, like maybe point to 10 possible mistakes, and then you can use that to update your paper. Now, a lot of those, I guess, this was not. I guess the current systems aren't great yet. They're making many mistakes. They are making themselves many mistakes, pointing to potentially errors that weren't errors and so on. But the bottom line is a result of interest in learning verifiers that can verify reasoning in natural language. Okay, and this is what we basically are trying to do in this work. And so we have this NeurIPS 25 paper where we provided the first work on learnability of verifiers for automatically checking reasoning. And again, I want to emphasize in natural language, which is of course complementary to systems like Lean or other systems that David is developing. Okay, and here is exactly what I mean, what we are trying to achieve here to become more concrete. So our goal is to train a verifier for the following task. So we have as input a problem statement and a sequence of reasoning steps. And our goal is to either output yes, the set of these reasoning steps are valid, so the trace is correct, or if it's a mistake, to output the location of the first mistake. So that's our goal here. And so for example, as an example, maybe our problem statement would be, please give me step-by-step instructions for booking my trip to NeurIPS. And maybe this is a sequence of reasoning steps, and we need to output the location of the first mistake, and the first mistake here happens at step 4 because in step 3 we are saying the agent says book a round trip to say United to Sydney from December 6th to December 12th. This is correct because this is what NeurIPS is this coming year, and these are the correct dates. But however, step 4 says book a hotel in Pittsburgh from December 6th to December 12th, so it's obviously incorrect. You shouldn't be booking a hotel in Pittsburgh if the conference happens in Sydney and you'll be in Sydney at the time. Okay, so the input is a problem statement and a sequence of reasoning steps that I have here on the left-hand side, and the output is the label should be either yes, the trace is fully correct, or otherwise point to the location of the first mistake. Okay, now to phrase this as a learning question, so my goal is to learn verifiers where I'm able to solve such tasks. And to phrase this as a learning question, I need some inductive bias. So I need to assume something, because otherwise learnability is not possible. I can easily prove lower bounds. Okay, and so our inductive bias in this case, in this work, this is our assumption, was that the proof can be verified easily, step by step. So this is what we assume. So in other words, the proof can be verified easily step by step, but as a human, I might not be able to describe to you exactly how I do that. But as in classic, using machine learning thinking, we're going to instead assume that there is a family of functions, call it a hypothesis class of functions, let's call them verifier, and this function takes as the input problem statements and the prefix of the reasoning trace, and we're able to tell us whether the last step of the reasoning trace is a valid step or not. And then we're going to assume that there is a target function H star in this class, which I'm going to call capital H, that agrees with the human oracle, with the human labeler, when applied on every instance X and any prefix of the reasoning trace that I'm supposed to verify. Yeah, so that's my inductive bias. Intuitive, it just says I can verify each step of the proof easily, or of the trace easily. So let me give you an example. So if I'm thinking about proof verification, H star, this target function, might encode how I personally would verify each step of a proof. And and it could be that if I'm verifying learning theory proofs, I have a different target, H star, than when I verify a game theory proof. And in fact, I might have a different target if I verify proofs of my graduate students compared to the undergraduate students in my class. Because to the undergraduate students in my class, I might give a lot less slack. Dravi and Sivet can tell you that I'm very, very careful with the proofs of my graduate students. Okay, so I could have different H star for different situations.
Quick question.
Yes.
So can we think of this as lean as well?
So I don't want to do lean, I want to think in natural language. And again, why is not lean? I cannot tell precisely how I verify the proofs of my undergraduate students. And I give a different amount of slack, it's just something I cannot mechanistically describe it to you.
So I can think
so
of
it's like a machine learning situation, yeah?
I can think of a mathematician that can read the proof, give me the lean code, plus a lean that has all the library to verify. And the combination of the two would be H. Like a human plus lean. A human that understands natural language.
I guess that could be an example. Okay, so it's fair, it's an example, but what I'm saying, I guess what I'm trying to emphasize, that could be an example, by the way. But I guess I'm trying to emphasize with my examples here is that there could be situations where I cannot tell you mechanistically how I verify. I cannot tell you exactly what H star is, but I can give you examples. Like I can take all the 5 years of grad school of Seed and Dravi and tell you, they had lots of drafts and I give them feedback on the drafts, but I cannot tell you precisely how do I give a new student feedback. But you can see the annotated drafts. You can see past examples. Okay, but your example is also a valid example. I'm just trying to emphasize there are situations or maybe the style of thinking I'm going to develop a formal verifier, like a lean verifier, might not be applicable. But these methods could be applicable. Does it make sense?
Yeah.
Cool. As another example, if you think about agent learning, H star, this I guess, could encode whether each step of the plan is legitimate with respect to users' preferences. So the current users' preferences. So for example, I prefer to fly United and I might not want to fly a Romanian airline. Okay, cool. So now, if our inductive bias is that there exists the target function, there exists target function H star that can help us verify each step of the proof, each step of the proof, and a natural approach for doing learning is to actually learn such a verifier from data, right? I'm going to learn a hypothesis H that takes as input problem statements and prefixes and returns yes or no. And then how I'm going to use it at the test time, I'm going to run it on all prefixes of a trace to determine the label on a new example problem statement or reasoning trace. So for example, in the example here in the left, the input is x tau 1 tau l, and I apply the verifier on the first, on the prefix of length 1, I get a yes, I move to the prefix of length 2, I get a yes, and so on, I then move to the prefix of length 3, here I get a no, and I stop and I say mistake a step 3. Or if for the prefix, this is one example where I have a mistake, or for the example on the right, I have, again, an input and the whole reasoning trace, and when I apply all the prefixes, I get yes all along, so when I put the label at the output is yes, correct reasoning. Okay, and then my goal is, how do I learn a verifier from past data to accurately, that's my question, the goal, how do we learn a verifier from past data to accurately verify new traces? Okay, that's the problem. Yeah, you had a question?
Yeah, do you have like a special end of sequence token or like a QED token or something like that? Because sometimes, when you're grading undergraduates or whatever, have a really correct proof, every line logically makes sense, but then at the end you're like, well, that didn't show what you originally wanted to show, right?
Yeah, so it's a great question. So so I guess if you do want to have, at this point, we really kind of, our model captures very well whether each step is a legal step given the previous steps, and really we are trying to emulate what the human would do on a sequence. Like if a human would only accept a proof, the final step after L, the final step will be yes, only the statement was proven, then we emulate that as well. But really at this point, like, we only emulate what the human would do on that. But it could be that the human would accept a plan without solving the original problem. So, like, mathematically, you are trying to learn to emulate, to do as well as H star. So I'm assuming there is this target H star target function in the family of verifiers, and mathematically what I'm trying to do is to behave like H star. Now, if H star has a property you mentioned, great. If not, we cannot promise you more than that. Cool. And so, like, you might wonder, okay, so now going back to the bigger picture story, why do you want to learn, why do you want to train a verifier? Why do you want to learn a verifier from data? Well, because intuitively speaking, a trained verifier can help to improve the accuracy and the efficiency of a pre-trained LLM generator. So in particular, here's a picture to keep in mind. We will have, when we train the verifier, so we might have a generator that is frozen. It's one of the LLM models. You might not have access to his weights. We cannot change the weights, but it's pre-trained. And so what we can do, we can still query it, and we can, the generator together with the user, the current user can work together to train a verifier, and the user can give feedback to train a verifier that is very useful for the current user. And then at the test time, at the inference time, let's call it the inference time, then the key point is that now once you have learned the verifier that is great for the current user, then the user can just send queries and hopefully get back send queries to the whole system where the generator and the verifier cooperate together, and then hopefully the user gets very accurate traces back on the problem statement he cares about. Okay, so that's kind of conceptually what we are thinking about.
So does it make sense to think of towers as kind of like reasoning tokens that you can plug exit? Should I think of? Let me actually keep my question until I see a little bit more.
Okay.
Okay.
All right. So how do you model this question mathematically? Like, how do you model the question of learning good verifiers for the chain of reasoning? And so in the original paper, so we have this new 75 work, where the most natural thing you try to do if you are doing learning theory is to build on the statistical learning theory, the PAC learning model. And so you can definitely model the problem of learning a verifier using these classic frameworks. So what we're going to assume is that we have a distribution over pairs of problem statements and reasoning traces, and we're going to assume that in the training phase, we're going to see a set S of IID samples of pairs, problem statements, and reasoning traces drawn at random from this fixed unknown distribution, obviously, over pairs of problem statements and reasoning traces. And we assume that this sample then is labeled by a human expert or human labeler, according to our learning tasks. So, for example, the first, maybe our expert will tell us that on the first data point, which is a pair of problem statement reasoning trace tau 1, this is a correct reasoning trace, so it's a yes, because it's tau 1 is a good reasoning trace for x1. Maybe on the second tau 2 reasoning trace, for example, x2, maybe there's a mistake at step 3, and so on. So, right, so in the training phase, we get an IID sample of pairs of problem statements and reasoning traces drawn IID at random from this distribution D over pairs of problem statements and reasoning traces, and then this sample goes to a learning algorithm, which then the learning algorithm hopefully outputs a verifier that does well on new IID samples drawn at random from the same distribution as a training set of typical instances. Right? So this is the classic statistical learning formulation. And, right, again, our goal is to output a verifier, a high probability output verifier that has low error over the distribution, meaning that for most of future examples drawn ID from the same distribution D, it correctly states whether tau was the legal reasoning trace, and if not, it gives a location of the first mistake. So classic goals. And turns out, actually you can prove a result of this type. You can ask, well, how many samples do I need in the training phase to achieve, to output a H that with high probability has low error over the distribution? And, you can just build it on classic statistical learning theory to get a result, a sample complexity that looks familiar, has 1 over epsilon in it, BC dimension of H times log L, or L is the length of the reasoning trace. And then we're going to go for the proof. If you are curious, it just follows from a shattering coefficient analysis. Is the shattering coefficient the class really care about the new loss function as a function of the shattering coefficient of the original class H, right? So we can just build on existing tools to get such sample complexity results. The problem is that these sample complexity results are not particularly meaningful for this problem. Okay, and why? Because if you think about how verifiers are then used together with the generator, so the problem is that when a verifier is used interactively with the generator agent, so the verified agent now is used interactively with the generator agent, we might go to distribution very, if the generator uses the feedback to update its output. So it can quickly get out of distribution, essentially. So pictorially, right, you can be in a situation where we have as input to the generator agent. Again, this is frozen, pre-trained, set the problem statement. The generator agent maybe generates, for this problem statement, a reasoning trace. And when the verifier agent says maybe the system step 2 is wrong, then maybe the generator agent goes and outputs a new reasoning trace where he modifies just steps 2 through L. Right, goes again to the verifier agent, maybe the verifier agent says step 3 is wrong. And now maybe goes to, again, the generator agent just modifies step 3 through L, and maybe finally here the verifier agent says yes, accept. But the problem is that now it might easily be out of distribution, and so this accept has no, like our theoretical guarantees don't tell us anything about us having done anything sensical here. Right, so because we can easily go out of distribution, the guarantees from statistical learning are potentially meaningless in such an interaction.
So Nina?
Yes.
Like even on your previous slide, I guess I didn't understand how you formalize the math of your theorem, because I'm not even sure what the space that we're talking about is when we're looking at.
So I can go back here. So I was trying to do this thing here, but I'm happy to also let me go back for a second to clarify. So so here, I think this is fully specified with a distribution over pairs, problem statements, and reasoning traces. We get the sample at random from a distribution.
Yeah, but that space is incredibly high dimensional, right?
Yes, so I'm talking about statistical learning theory here. So you can get sample compressed bounds. I'm not saying you'll have an efficient algorithm necessarily. But typically statistically, machine learning, the very first thing you get sample generalization guarantees. I'm very worried about computational efficient algorithms. But my first point is, even the statistical learning guarantees that you get will be meaningless because now we don't have a learning algorithm just in its own word like in classic learning theory. We're trying to use a verifier to improve the generator. And because of that interaction, this idea assumption that we crucially make in statistical learning will be easily violated. That's the point I'm trying to make here.
Okay, so I can ignore the fact that you wrote a theorem here. Maybe that's not an interesting theorem.
I'm happy to tell you all of it about it offline. It's not, it is a reasonable theorem. It's technically not very hard to prove, yeah. I'm happy, because I put a disclaimer at the beginning.
Maybe the point is just the BC dimension of H is just unreasonable.
Not only it's unreasonable, if I'm trying to apply this theorem, like I'm going to basically violate this theorem has like it only like because it says the training sample, like the conclusion of this theorem is that on most future examples from the same distribution as a training set of instances, something will happen. I'll correctly either say the reasoning trace is correct, or I'll point to the location of the first mistake. And this will happen on most axes. But when I try to apply this, the conditions of the theorem are not satisfied in the real world, which I'm trying to use when there is interaction between the generator and the verifier. That's what I'm trying to say. Okay, but again, if you're curious, I have to tell you about it offline, all the details. Okay, cool. And so now, so actually in our original paper, we had some fixes. We tried to have some fixes for this situation because, clearly the statistical learning theory framework is not a good framework for learning verifiers. And in our original paper, we had a couple of proposed models. I'm not going to go through those right now because there are gaps. I don't think they're even in the upper and lower bounds, and I don't think they're also the most interesting. And instead, I'm going to tell you the most recent results that we just posted on arXiv a week ago or 2 weeks ago. We take a very different approach, and we kind of go at another extreme, which is online learning of verifiers. And again, this is joint work with Iwanji, Avrim, Dravi, and my current student, Corina. Okay, cool. So now we're going to take an adversarial learning, kind of online learning approach. So I'm not going to make any distribution of our problem statements or the pairs of problem statements and traces. So make no assumption even about the distribution of problem statements. And here is how the interaction we're going to, conceptually how the interaction we're going to go. So we're going to assume that we have an expert, a human, maybe Jason. He has a problem statement. We're going to feed into the generator, and the generator outputs a reasoning trace. Now, on the other hand, we are trying to train an algorithm for learning a verifier for problem statements coming from this user, for example. Okay, and so the expert fits in the problem statement x1, the generator generates, which is again pre-trained. The generator generates a reasoning trace tau1 for this problem statement x1, and then our algorithm for learning the verifier has a current verifier, a current hypothesis of what a good verifier would be, and applies that on the pair x1 tau1. It might tell us, no, there is a mistake at step 3. Then now, because we are training this algorithm for learning verifiers right now, the expert might tell us, no, actually, what your hypothesis told me currently, that there is a mistake at step 3 is incorrect. Actually, the trace was a good trace for this problem statement. Okay? And then we get feedback, so the algorithm gets here feedback, and sorry, the algorithm now gets feedback and updates its internal hypothesis, and then the whole thing repeats. Maybe we get another problem statement x2 from the user. The generator generates a reasoning trace. Our algorithm for learning the verifier has a current hypothesis, applies it, and tells us, no, it's a mistake at step 4. And maybe the human looks at what the algorithm said here for learning the verifier and says, yeah, correct, and so on. And everything repeats, right? This is kind of the model. And so now we're not going to make any assumption that the problem statements are drawn from a distribution for now. And all we're going to do are trying to ask, can we bound the number of mistakes that this algorithm for learning the verifier makes?
Quick question.
Yeah.
Just a clarification. So if the trace is wrong, but then the algorithm verifier was wrong about the step of the mistake.
Then you update. Then you get some feedback. And by the way, in the paper we have various variations. Like we have 3 models, but let's keep simple for now. Like if you make a mistake with the location, you update. Yeah? Because you can have, there is also, you get feedback that there is a loss function, and we have multiple loss functions in the paper. But for now, let's keep the loss function that I had in mind. You really have to point to the correction of to the location of the first mistake. Yep.
This also makes sense, not only tell the generator that you are mistaken, but somehow explain why it is mistaken.
That's a fantastic question. We don't incorporate that.
The nature of the mistake.
Yeah, this is very new work. It's a fantastic question. We are not doing that, but it's going to be a great open question for the future. Right? So I'm just putting, this is very, very new work, so it's not, we didn't analyze deeply about it, but this is great point though. And AI people and LLM people totally agree with you, but that would be a great feedback to give back. Yes?
You're sort of moving to an online analysis here.
Yes.
Would a statistical analysis also work in this setting where you're assuming a distribution on the problems? Is it important that for the theory that you're moving to an online?
When we then try to use the generator, because I'm going to show you, so right now I'm going to show you the model. I'm going to tell you a type of theorem we prove, and then I'm going to try to go back to show how you can use this together with the generator. And then, I guess to get the results, then we're going to assume a distribution, but then over instances, we're going to do a mistake-bound to pack conversion. But for that reduction to work, we do need to assume that these are truly online, truly adversarial. Right? So, I mean, it's just, we will at some point we need to really use that, but yeah. But you can also.
To me now, like I could have made a statistical or some,
We could. There are many. You can do distribution online, right? But we are doing fully adversarial because we need that actually. What we're doing is like, yeah.
So just to clarify, the feedback from the expert labeler is still yes, no. So if the algorithm says no, the proof is wrong, the mistake is in step 2, and the expert labeler cannot say that the proof is wrong, but the mistake is actually in step 3.
No, let's assume that we get actually full feedback. So full feedback is we get, if it was wrong, what is the location of the mistake?
Okay.
I mean, even when you do online learning, you can have full feedback, you have banded feedback, semi-banded feedback. Let's assume for now full feedback, okay, just to use technical terms. And by the way, just also to point out, this is just, we just started to analyze these situations. So there are many open questions, so hopefully you guys can join and think about it. So it's not something worked on for 10 years, it's very new work.
Can I ask one more question?
Yes.
So you were talking about this interaction between the generator and verifier, but in the picture in the previous slide, that interaction does not exist. So you're just like feeding the problem statement again and again to the generator. So it's kind of a different setup compared to that interaction between the generator and the verifier, if I understood correctly. Right, so that interaction doesn't happen in the previous picture.
It does, why not?
I mean, you're just rerunning the...
Oh, I see, yeah, because I said if it's incorrect, because I'm telling you how I'm training the verifier right now. But in the real world, with the inference time. So so this is a model for training. So what I'm showing you here, it's a model for training the verifier. But that was the interaction that I was showing is the test time or the inference time. So now this is a model for training the verifier. Yeah. Cool. And so so I have a couple more topics, so I have to slightly speed up here. Cool. So while we're doing the online learning model as well, let me tell you what guarantees we provide. And again, this is just, I think they are very interesting guarantees, but it's the first cut at thinking about this problem. And so when you do online learning, you want to bound the number of mistakes. One interesting twist we do here, we distinguish between the soundness error and the completeness error. Soundness error means informally you accept an incorrect reasoning trace, and completeness error means reject a correct reasoning trace. And often these soundness errors could be more catastrophic than completeness errors, like in medical diagnosis. It could be with more catastrophic consequences. So that's why it makes sense to try to provide defined trade-offs to distinguish between the two of them. And in the paper, we have a couple of such defined trade-offs. One of them, the simplest one to think about, maybe we are trying to design an algorithm for learning a verifier to minimize the total number of mistakes, subject to have a budget on the number of soundness errors. Okay, and for this, and again, I'm not going to tell you lots of details, but for this we have the following type of guarantee. So we show that for any k, and again, k is an upper bound of the number of soundness mistakes, we show that there is an algorithm that makes at most k soundness mistakes in total, and at most something called SC to the stone dimension of h with parameter k total mistakes. So for any k, if you're is an upper bound of the number of soundness mistakes, we show you an algorithm that can make at most soundness mistakes, and it makes at least this, at most this many mistakes. And this is a new notion of dimension. We call it SC to the stone dimension of h and k. And the interesting thing is that this is optimal. So basically, we provide an optimal algorithm for this setting. We are trying to minimize the number of total mistakes subject to a budget on the number of soundness mistakes. Okay? And now, yes?
Just curious, like if you recognize the proof is wrong, but you said the wrong step is wrong, does that count as a soundness mistake or like a?
So, okay, to be precise, so I was trying to stay informal, by the way. So soundness error means you say no too late, and completeness you say yes too early. Okay, think about it that way. Yeah, I'm just trying to use informal terms, but you guys are a very sharp technical audience, so I cannot get away with that. Good. All right, good. So now for the next 2 minutes, so I'm going to try to speed up because I also want to tell you a lot about a couple of other topics I think are also very interesting that I mentioned at the beginning. So now this will be just for the learning theory experts, and I know there are some in the room. So for 3 minutes or 5 minutes, 3 minutes, if you are not a learning theory person, don't worry. So I just want to mention what is this new notion of a dimension. It's called SC to the stone dimension. It's been found as completeness in the stone dimension. And so I'm going to tell you what the definition is. And so, when we do learning theory and we do statistical learning, we use VC dimension. We talk about shattering points, right? But when we do online learning, we talk about shattering trees. So let me tell you what the notion is once we start shattering trees. So what is an SC mistake tree? So this is a new notion that we introduced. So what is an SC mistake tree? Now it's a rooted binary tree that has the nodes are labeled with pairs. That might be given as input to a verifier. So these are pairs of problem statements and reasoning traces. And then each node has 2 children, a no child corresponding conceptually to soundness error, and the yes child. So two edges, a no edge and a yes edge. And then, sorry, am I going that direction? And then we're going to say that the tree is shattered by hypothesis class H if for any root to leaf path there exists a hypothesis in my class that agrees with the edge labels on that path. So in particular, there exists, so for example, for this path here, there exists, say, H2, that has a property that H2 when applied to x1 is yes, corresponds to what I see here. H2 of x2 tau 2 is no, corresponds to what I see here. And H2 applied to x3 tau 3 is no, which again corresponds to what's here on the edge. And so if that's the case, but for any root to leaf path, there exists a hypothesis in my class that agrees with the H labels, and I'm saying that the tree is shattered by the hypothesis class H. So, for example, here this tree is shattered by these 4 functions, H1, H2, H3, H4. Okay, and then what is the SC to the stone dimension of H and K is the largest M, such that there exists an SC mistake tree shattered by H, such that for any root to leaf path that has at most k no edges, which conceptually corresponds to soundness mistake, any such path has length at least m. Okay, so the S-series non-dimension is, and if you think about it, you can easily show that you can make any deterministic algorithm to make at least m mistakes if the S-series non-dimension of h and k is m. But the cool fact is actually there is also a corresponding algorithm. So you can show that for any k, there exists an algorithm that makes at most k soundness mistakes, and the number of total mistakes is at most S-series non-dimension of h and k. Okay, so this is an optimal algorithm for this setting. Okay, so I know this was very quick, but if you're curious, this provides the bottom line is this is an optimal algorithm for learnability, online learnability of verifiers in this setting. And if you're curious, come and talk to me. I'm happy to tell you all about all the proofs of mine. Okay, but now going back to the bigger picture story, let's see how this can be used to improve a weak reasoner, right? Because remember, the goal is to learn a verifier to then have it cooperate with the reasoner or the generator. Okay, and so just to give you a sense, again, I'm not going to go into full details, I'm just going to give you a sense of the type of result we provide here. So let's assume that we have an alpha weak reasoner, right, or generator. Like these pre-trained LLMs are so fantastic, they've been trained a lot of data, but on a new task, they're not going to be perfect, but they're going to have some good signal in them nonetheless. Okay, so let's assume that we have alpha weak reasoner for the problem statement X, so for a problem statement X. So let's assume what that means that on that problem statement X, we have probability at least alpha of producing a legal next step that agrees with the human target function, conditional on the steps being correct so far. Okay, and so if you think about it, that means that if I feed in X to my reasoner, there is an alpha to the L chance, at least alpha to the L chance of producing a fully a legal reasoning trace. But now, of course, if I'm doing best of n, which is what applied machine learning people do, I keep generating reasoning trace and verify them until I get a good one. At the end, I verify them at the end until I get a good one, then I might need 1 over alpha to the L traces, exponential number of traces, right? If the goodness of this reasoner on the next is this property that I'm mentioning here. But instead, the key idea of our work is to use the train verifier step by step to help the reasoner build a correct trace, a correct proof sequentially. So in particular, if a step is not correct, say step 1 here is not correct, the verifier informs the reasoner to retry. Okay? And so the key point is that if we do so, we only need a linear number of calls to the reasoner. So only L over alpha calls to the reasoner. Okay, and here you see that the interaction happens between the verifier and the reasoner once I use it at the inference time. Okay, and I'm not going to go into the details, but you can read them in the paper. So the whole point is now we then use guarantees. Like the question is how many samples do you need to train such a verifier, right? Now we're going to make an assumption with the reasoning to train the verifier and to apply it in this specific case. We're going to make assumptions that the problem stems come random from a distribution, and we're going to ask how many samples do I need to train the verifier and how many calls, and then the paper talks about that. And the proof, roughly speaking, goes from mistake bound to path conversion at a high level, for those of you that are familiar with learning theory.
How does this fit exactly into the adversarial online learning problem for learning the verifier? Timing-wise, like, should I just think of, hey, I'm going to first run my adversarial online learning algorithm to learn a verifier at time?
Yeah, so at the training time, I'm going to train the verifier, and I'm going to run through this process exactly. So at the training time, like what I have here, on the instance X, the reasoner generates an X, the algorithm for learning the verifier gives me a hypothesis, and I keep doing it, and then I build a trace, and it's either correct, the human tells me it's either correct, or if not correct, tells me the location of the first mistake, and I update the algorithm, and so on. So I use the online learning algorithm at the training time, and I train the verifier. And then I generate a sequence of hypotheses, and then you use a classic mistake bound to path conversion, or you then test the sequences hypotheses generated on a new fresh set of samples of problem statements. And then I pick the best one, and then that is what I then use at the test time.
And the reason that we are using adversarial online learning is because we are learning a verifier that
is
not tied to
interaction.
a certain distribution, because that distribution of training might be different from the distribution that basically is.
Even when you train it, the question is what's the distribution really? Because it's not a distribution over, the distribution over X might be changing. If I have a distribution over X, the distribution over X on which I apply the verifier might be changing here. So that's why you...
I meant the distribution over X and tau.
X and tau, yeah.
So that seems like completely different here.
Yeah. Okay? Cool. So again, I'm happy to tell you lots of details offline, and I'm happy to, and these are just the theorems we have currently, but I'm sure we want to write other interesting theorems. To summarize this part of, sorry, I'm keep going. So to summarize this part of the talk, so we provided work on learnability of verifiers for checking reasoning in natural language, and we already have some, I think, cool results. But there are many interesting open questions. So for example, for now, we still assume that H star, that there is a perfect H star in our class. We assume the so-called realizable case. Can we do something interesting in the non-realizable case? Actually, I started the project with one of my students and somebody else at CMU on trying to use Plug-based bounds that they pioneered in this context, which I think are very relevant. But of course, we can also ask, can you provide more efficient practical algorithm, or algorithm even for the simple case or the realizable case is optimal? It's of course not super efficient. So can we actually analyze practical algorithms that also enjoy very cool guarantees? And also, can we actually, so what I think it's cool from a learning theory perspective, we have is two agents, the verifier and the generator, and they cooperate together to produce good outputs. But there could be other agents. Actually, if you look back at the Alithia paper that I mentioned at the beginning, they also have a refine agent. So there could be other interesting questions there as well. Okay, cool. So now I'm going to switch topic. But now the rest of the talk will be more high level. So yeah, good. So I'm going to switch topic. It's mostly describe problem formulations that I think are very interesting these days. And so the next topic I'm going to talk about is, again, multi-agent systems, but now the agents are strategic. So like you can think conceptually the verifiers, the generator interaction, that there's no, we're cooperating. But in many situations, the agents might be strategic. And in these situations, what do? Classically, first of all, learning theory analyzes a single learner in its own word. Now, what game theory does analyze learning in the presence of other strategic agents, and looks at static solution concepts like equilibria, or it looks at learning very simple learners, so in particular things like fictitious play, best response, better response. But the bottom line, there is often no feature information, just actions, right? And if you are familiar with machine learning, you cannot even think about doing machine learning without lots of high-dimensional features. Okay, classic game theory doesn't incorporate that. And so, obviously, to analyze learning in the presence of other strategic learners, it's important to kind of build on both game theory and learning theory, and to analyze learning in the presence of other very sophisticated learners. And in this talk, I guess in the next 5 minutes, I'm going to tell you the type of results we were able to provide in the past 10 years for strategic situations with commitment that are used in security applications. Okay, so what does it mean? So now it's a technical term for this. It's called something called stackable games. So here we have what is a strategic interaction with commitment. So we have two players. One of them is the leader, and the leader is able to commit to a strategy before the follower takes an action. So as one concrete example of a game, think about security games. And here we have a resource-constrained defender trying to stop the attacker. So for example, and this, by the way, this has been used in the real world by, they were pioneered in the real world by Miguel Hampek, who I think was a speaker in the same series, the previous speaker in the same series here at TTIC. And so the examples he worked on for airport security, the leader is a defender, or the leader or the defender is the TSA, Transportation Security Administration, and the attacker could be a terrorist. Okay, or another example that Miguel's group worked on, in wildlife protection, the defender, so the defender now, which is the same as the leader in security games, is, this could be the park rangers, and the follower or the attacker will be poachers. Okay, and so basically in stackable games, we have interactions between a defender and an attacker, and the defender has a strategy space, which is a deployment of resources to protect targets. This could be randomized deployment to protect targets. And the attacker has a strategy space which target to attack. And what's the stackable solution concept is, well, we're going to assume that the defender commits to a defense strategy first, and for example, a randomized patrol strategy through the park, and then the attacker best response. And yeah, this is a stackable solution concept. It's introduced in economics for the first time, studied in computer science by my colleagues at CMU, Vince Konitzer and Thomas Handel. We talked about computing equilibrium, the one-shot game, and then there is follow-up work by several people, including Abrim here, and where they looked at like learning the optimal strategy for repeat interaction with the same attacker. You might not know the utility of the attacker, but it's the same attacker that comes back every day. Okay, and again, this has been, so the prior work provided theoretical results of this forum, and also like showed it can be relevant, these results can be relevant for real world applications. Like in our work, we extended the line of work in two different ways. So first of all, we looked at repeated stackable games in face of several different types of attackers. So maybe, so again, the interactions will be potentially repeated. And then we have different types of followers showing up every day. So this is an older work with Arn, Mika, and Ariel. But in more recent work, which I think is also really interesting and closer to more modern AI, is we also consider online learning in repeated contextual stackable games, right? Where now the players are using rich context and feature information when they think about how to act. Okay, and I guess just very, very, very briefly, so the type of results. So we have, so going back to the 2015 result, our early result on this topic, we have a repeated interaction between a defender and a sequence of attackers. The defender first commits to a mixed strategy P1, the attacker best responds to P1, and the defender gets some utility, but depends on the target attacked and what they played. The same interaction repeats next day, the defender commits to a mixed strategy P2, when another attacker might show up, A2 maybe, attacker type 2 might show up, the attacker A2 best responds to what the defender has done, and then the defender again gets some utility. And then this keeps repeating for say capital T times steps, and what you want to do, you so you are the defender, and you want to learn how to defend. What you want to do is you want to learn how to compete with the best fixed mixed action in hindsight over the realized sequence of attackers A1, A2, A3. And so mathematically, you want to achieve no regret. Which so what is the regret? Is the difference between the utility of the best P in hindsight, the best mixed strategy in hindsight, the utility of the algorithm of the sequence A1, A2, AT, the realized sequence, and we want this to be sublinear in T. Okay, and I'm not going to go through all the details, but just want to tell you why is this an interesting machine learning theory question? Well, because turns out you think about it, and you can show this even in simple security games, the utility function of the leader is, as you vary the mixed strategy of the leader, that has sharp transition boundaries. Okay, so it's not convex, not nice in classic machine learning theory, so you cannot apply off-the-shelf online learning techniques because the utility function is going to have sharp transition boundaries. And so what we do informally in that work, we somehow carefully explain the structure of the problem and to identify some set of experts to then reduce to more classic online learning problems. Okay, and this was the 2015 paper that we had, but again, this one didn't have actually feature information, but we have more recent work with my former student King Harris and Stephen Wu and several other collaborators, and also my current student Florina. And we also have recent work where we actually also incorporate stackable information or feature information or context information. And so that's interesting because now, and again, skipping the details, now we're going to compete, rather than competing with the best mixed action in hindsight, we're going to compete with the best policy that maps features over actions. Okay, and there are several papers because actually it was very non-trivial to get the right results. But there are several papers on this topic, and I'm going to skip the details. Turns out that once you have context, you cannot even do anything if you really assume that both the context and the possible attackers are chosen adversarially. Then no regret is not possible. But then you have to impose a little bit more, a few more conditions, and we have examples of sufficient conditions in our work doing that. Okay, so the problem becomes very interesting mathematically. Okay, and of course I skipped the details. You have full information, bandit information, and so on, like when you think about the feedback you get. That's why we have several papers on the topic. Cool, but to summarize this part of the talk, so basically, this is an interesting example where we looked at strategic learning in strategic settings, and where the agents might be more sophisticated agents and potentially use also context information or feature information. And of course, it would be interesting to think about learning in the context of other strategic learners through the lenses of modern AI in other settings as well. Okay, and I do have 4 more minutes, which is great, because now I can tell you again at a very high level a couple more results. So this is a topic that we worked on a lot. I think it fits it connects nicely to the bigger picture where we're learning in the presence of other learners, potentially very complex objects. So and I want to mention a couple of words about this as well. So it's learning algorithms for solving problems that remain intractable within classic frameworks. And actually, both of my students sitting here on this have worked on this topic. My former students. Yes, and so at the high level here is a story. So now let's step up a little bit and think about not only machine learning algorithms, but more general, think about algorithm design in general, maybe pricing problems, auction design problems, logistics, scheduling, clustering, so different types of problems. So what do people normally do when they think about algorithm designs in the setting auctions? What people do in the setting, they normally, so if they have a problem that you want to solve, and they assume you have a brilliant scientist, a genius scientist sits down and hand designs an algorithm, right? This is the classic approach in computer science, economics, OR. And then if you're a computer scientist, maybe from a theory point of view, the algorithm designer, we're going to think about worst case analysis. How well does the algorithm do on worst case instances of the problem? If you're an economist, you might assume a prior, but in all of those cases, often, the guarantees that we can get for hand-designed algorithms are often very weak. We can show lots of lower bounds. Sometimes we have no idea how to improve the upper bounds. So things are very hard if you get stuck with hand-designed algorithms. And so now what happens in the real world often, people think about, well, because classic theory is hard, so let's try to use machine learning for algorithm design, right? This is what became very popular. So people looked at it in the AI community even in the 90s, like Eric Horowitz, Bart Selman, and so there's a group that looked at it early on, Kevin Leighton Brown. But this actually, let's use machine learning for algorithm design has become very popular in the past decade. Okay, but now of course AI and machine learning are moving very, very quickly. Now, 3 years ago, it was like, oh, let's use LLMs for algorithm design, and this year, it's the buzzword is we're going to use agents for algorithm design. Okay, so which is a good idea, except that the beauty of the classic algorithm design is that you can provide guarantees, right? So our brilliant scientist was able to sit down and work carefully, very hard to think about how do I provide provable guarantees for my hand-designed algorithms. And so if we're going to use machine learning for algorithm design or agents for algorithm design, can we provide any guarantees, right? And that's a question that we've been thinking about a lot in the past 10 years. I guess we were thinking about machine learning for algorithm design because it started 10 years ago. And the cool news is actually, without going into a lot of details, we have very strong, I guess now we have very cool general results that I think are widely applicable. And so intuitively, the type of question we are asking, if you're gonna, for some problem that you want to solve, if you're gonna have access to past instances of the problem, and then you're learning an algorithm from a large parametric family of algorithms, what guarantees do you have that this algorithm is gonna do well on new instances of the problem? Okay, that's intuitively the question that we've been asking. And the news is that we have we have general results. So initially we looked at case study by case study. We looked at learning how to tune mixed integer programs, solvers from mixed integer programs. So you see that Mellon. We looked at learning how to cluster, and so on. We looked at learning how to build decision trees with Dravi. So we looked case study by case study, but turns out that there are also very general kind of proof techniques that you can extract that you can then apply in new domains. And so without going through all the details, this is a picture that you can take from this part of the talk. So what we're able to show is that, so first of all, just like for security games, remember I told you that what's hard in security games is that the utility functions, so I fix an instance of the problem, the strategy for the leader, the utility function has sharp transition boundaries. The same thing will happen here. If I fix a problem and vary the parameters of the algorithm, the corresponding loss function have many sharp transition boundaries. Like if it has lots of sharp transition boundaries, nullability is possible. But what we're able to uncover is that we often, by looking at case studies, that these, what we call them dual functions, are somewhat structured. So they are piecewise structured. And so we're able to, so in a lot of these domains, the dual functions are piecewise structured. And then we wrote general theorems that say, well, if your dual function is piecewise structured, then here is how many samples you need to learn a good algorithm. Okay, this is a way to think about such a theorem. And this is an example of structure here. There are other piecewise structures people looked at, for example, and I'm going to skip that.
And these are integer programs that they have some LP relaxation?
Yeah, so we applied in many different settings. So like one setting is in the OR, learning how to solve mixed integer programs using a branch and bound and branch and cut. So we've done a lot of branch and bound, my former student is now Professor at Stanford, we've done a lot of branch and cut. But this is one case study, but we also looked at mechanism design. And by the way, this idea of using machine learning to solve some hard question, like mechanism design question, originates from Jason. He's sitting here in the room with, when I was a PhD student in 2005, we had a Fox paper, we're looking at a simpler case, but we used we had a paper called Machine Learning for Mechanism Design. We're looking at unlimited supply options, and I think Jason was the one that came and talked to Ari, we should use machine learning for auction design. Now, it turns out you can elevate it to machine learning for algorithm design globally, and you can apply not only to mechanism design problems, but to OR problems, to hyperparameter tuning machine learning, to scientific computing. So, for example, we had to work on learning hyperparameters of linear system solvers, and so on. Even in theory of computing, like you like to do a lot of or you used to like to do a lot of like randomized rounding, for example, right? You can learn how to round. We had an example here on this paper, so you can apply it broadly. So for almost any algorithm problem you can think of, there is natural rich parametric family of algorithms, and you can try to learn an algorithm that does on your type of instances. Okay, cool. And again, so if you're thinking about such problems, come and talk to me because we have very general tools. So, like intuitively speaking, and I just gave you a bit of a flavor to show in a lot of these case studies of duals, if I fix, for instance, the problem very the hyperparameters, there are piecewise structure, and the structure can be expressed in different ways. This one by a picture this way, but there are other ways, and we can analyze them. And the corresponding map is very cool. I had a lot of fun thinking of all my PhD students because many of them worked on that. And it was not only statistical and computational, but like Ravi had to read algebraic geometry, differential geometry, and so on to analyze some of these algorithms. So if you love math, you're going to love it around work too. Okay, cool. And like in terms of open questions, so what are major open questions here? I actually do think, because again, the people right now talk about I'm going to use agents for algorithm design as opposed to, or LLMs they were saying but 2 years ago, but now it's agents for algorithm design. So I'm going to ask an agent to help me to design an algorithm. And so how is it different? So maybe this goes back to actually to Sasha's comment earlier and for verifiers, but when you think about algorithm design here as well, so maybe that you can communicate with the AI agent not only through, like in machine learning for algorithm design, I'm assuming that I have access to past instances of the problem. This is what I give to the machine learning algorithm. Past instances of the scheduling problem. For example, I give it, here's my past instances. Okay, but now maybe when you are doing agent, maybe you can also give more description. Maybe you know something new about, maybe you can in words describe something about your instance that maybe the AI system should be able to incorporate. So in addition to past instances of the problem, maybe you can give in text something that you know more about the instance. Okay, and so actually, my former student Ellen, who was on this line of work, she actually had her students they showed how you can, for cutting planes actually, her students did experiments where they interact with the LLM agents by describing the structure of the current problem. And apparently, without any past instance of the problem, without any training, she was able to produce promising cutting plane families, and so was able to solve the MIP very fast. So people have done this empirically. Can you provide anything interesting theoretically? I think it's a very interesting question because the question is how do you even phrase the question. It's definitely relevant for the modern day. I've seen more and more people saying, I'm going to use agents to help me schedule things for databases, or Ellen has her students talking to the LLM to output good algorithm for cutting planes and so on. And I guess I had this on my slides for some time now. I think even when I gave a talk at the workshop, like in 2018 here, and I'll be very, very curious if machine learning for algorithm design or agents for algorithm design eventually help us uncover algorithmic paradigms as well as proof techniques that humans were not able to design before. I mean, fundamentally new ones like LP relaxation or greedy or divide and conquer. Can we discover new algorithmic techniques by using AI? I had this, I think, 7 years ago. I don't think it has been solved yet, but it's very cool if it's solved. Okay, but I'm going to stop here. So, AI is very, I guess, machine learning these days are very, very exciting. We need a multifaceted approach. It's us trying to argue with 3 different line of works. And I'm going to stop here. I think if you want, we can stop with this quote. More questions? Yep.
In the first part of your talk when learning verifiers, in general, as the sequence length L got bigger, learning was more expensive, you needed more responses or more samples. Whereas intuitively maybe, if we think about NLP data sets, as these sequences get longer, each data sample now contains a lot more information. So I'm wondering, have you thought about maybe structuring your assumptions on the sequence to try to, is it fundamental that learning gets much harder in general as our sequences
so
get
it's
longer?
a good question, but to be honest, in our model it didn't get more difficult. So in the first result we had a log L, but in general it didn't get more difficult because we did make an assumption that each step is easily verifiable. So I'm assuming that each step is verifiable by the same H star. So actually it didn't get harder, but there's a question that I've gotten in the past, people say, like in applied machine learning, people will say, oh, the longer the sequences, the harder it is to learn. But in our framework, actually it didn't get harder.
But like your sample bounds get more expensive, or like your number of responses gets more expensive.
There's still log L dependence.
Well, we don't know if it's needed. It's a minor order term, but we don't know if it's needed. But I guess, okay, maybe there is some dependence on L, but not a lot. Because we actually, and it's also because of our inductive bias. We assume that H star that verifies just step by step belongs to the same class. There could be other learning scenarios where they could be much worse.
Fair.
But it's a good point. Like, yeah, so how, yeah. But you are saying it can get easier. Like, I guess we didn't explore that either, but yeah.
One last question, maybe?
Yeah, one of the main downsides of sort of LLMs for proof writing compared to humans is this sort of lack of certainty, right? That if a student tells you a proof and he's very uncertain and he's been cooking it like in sort of at night, etc., he can tell you, oh, this is a bit sketchy, you have to look at this very carefully. I was wondering, have you guys at all thought about sort of incorporating some notion of confidence in the steps? So like the LLM says, this is wrong almost certainly, or perhaps could be wrong, it could be right.
So our theorem, which I don't have here on the slide, but the guarantees we keep in the end, because that's exactly the point. Because we do have this soundness and completeness trade-off, which is our algorithms are not super practical in the online learning world, but they have very interesting guarantees. So actually we do address this under our assumptions, exactly what you are saying. So let's see if I can pull out a theorem. So the answer is yes. The fact that we distinguish between soundness and completeness error. So in the end, like we might say, I don't know, the system or the reasoner works together with the verifier. On some examples, you might say, I don't know, and if the probability to output reasoning that is incorrect is very small. So I guess what I'm saying, our distinguishing between soundness and completeness errors allows us to give very strong guarantees. Which is one of the reasons for which I like having this difference between soundness and completeness errors, because it allows you exactly to address the types of problems you are mentioning. Now, again, our algorithms are not super practical, to be fair, because for our version space algorithms, it's very interesting to try to develop algorithms that are more practical in that direction. But it's one of the reasons for which I like the soundness and completeness.
Great. So we should probably end here. Thank you, Nina.